Hello, students, and a massive congratulations. You know, we've just officially completed all the concepts of Chapter 4, carbon and its compounds, and that is a huge milestone. But the journey of chemistry definitely doesn't stop there. I want you to just look around you right now. Literally everything around us. The air we breathe, the water we drink, the iron in our buildings, the gold in our jewelry, even our very bodies. It's all made up of elements, and scientists have discovered more than 100 of these elements. But imagine how impossibly difficult it would be if we had to study each and every single one of those elements completely separately. So today, we are jumping straight into Chapter 5 of Class 10 Science, kicking off a brand new explainer to learn exactly how scientists first tried to organize all this chemical chaos. Okay, here's our roadmap for today's explainer. 1. The chaos of elements. 2. Dobereiner's rule of triads. 3. Newlands musical octaves. 4. The search continues. And finally, 5. Quick revision and exams.
All right, let's jump right into Section 1, the chaos of elements.
To really wrap our heads around why we need to classify things, I want you to picture your school library. But not just any normal library. Imagine one with thousands and thousands of books arranged entirely at random. You've got a dense science textbook sitting next to a fantasy novel, right next to a baking cookbook, just scattered across the floor and shoved onto shelves with absolutely zero system. If you walked in there, would it be easy to find one particular book? The answer is obviously a big no. And you know, this brilliantly illustrates exactly why elements need classification. Just like those books, elements have to be arranged systematically. A solid classification system is a total game changer for 4 reasons. It helps us study elements easily without getting completely overwhelmed. It allows us to instantly compare their properties. It remarkably lets us predict the properties of elements that haven't even been discovered yet. And it helps us uncover the hidden relationships among different elements.
So, how do they do it? Let's move to Section 2, Dobereiner's rule of triads.
Way back in 1829, there was this German scientist named Johann Wolfgang Dobereiner. He started noticing that certain elements seemed to behave almost identically, kind of like siblings. And this gives us an absolutely crucial definition for your exams. A triad is a group of 3 elements having similar chemical properties.
Now, what's really fascinating here isn't just that he grouped them, but the underlying math he found. Dobereiner jotted down the atomic masses for his very first triad. We have lithium with an atomic mass of 7, sodium at 23, and potassium at 39. These elements all reacted similarly in the lab, but Dobereiner discovered a literal numerical secret hidden right inside their weights.
Check out this remarkable math trick. If you take the atomic mass of the first element, lithium, at 7, and you add it to the third element, potassium, at 39, you get 46. Divide that sum by 2 to find the average, and boom, the result is 23. That exactly equals the atomic mass of the middle element, sodium. It was a total mind-blowing revelation back then that chemical properties and atomic mass were secretly linked.
And the craziest part? It wasn't a fluke. This perfectly holds up again in his second triad. If we take calcium at 40 and barium at 137, that sum is 177. Divide that by 2, and the average mass is 88.5. Look closely at the middle element there, strontium. Its mass is 88. The average is approximately equal to the middle element. For a second there, it really seemed like Dobereiner had completely cracked the code of the universe.
But, well, there's always a but in early science, right? Every early solution has a fatal flaw. While he successfully grouped elements with similar properties and proved that incredible relationship between mass and properties, his system had severe limitations. The major roadblock? Only a very small handful of elements could actually be arranged into these neat little triads. Most known elements simply could not be classified this way. Imagine trying to organize that giant library we talked about earlier, but your brilliant new sorting system only works for about 9 books. It just wasn't going to cut it.
Which perfectly leads us into Section 3, Newlands musical octaves.
Fast forward a bit to 1866. An English scientist named John Newlands decided to arrange all the known elements in increasing order of their atomic masses, from the absolute lowest to the highest. And when he did that, he discovered an incredible new pattern, giving us Newlands Law of Octaves. This law states that when elements are arranged in increasing order of atomic masses, the properties of every 8th element are similar to those of the first element.
He actually compared this to playing musical notes. You know, on a piano keyboard, after every 8th note, the sonic pattern repeats itself. Well, if we start counting from lithium as our first element, the 8th element down the line is sodium. And just like musical notes, lithium and sodium share incredibly similar chemical properties. The exact same thing happens with fluorine and chlorine. It was like the universe had written this grand chemical symphony.
So you're probably thinking, he nailed it, right? Actually, scratch that. While Newlands successfully created a systematic arrangement and grouped similar elements together, his musical law eventually completely broke down. The limitations were incredibly steep. See, it was only applicable up to the element calcium. The music literally stopped at calcium. After that point, every eighth element did not match the properties of the first. Even worse, his table was so rigid that it couldn't accommodate any of the new elements that were being discovered.
And that brings us to Section 4. The search continues.
To force elements into his octaves and just make the music work, Newlands actually started doing some very questionable, unscientific things. He placed entirely dissimilar elements right next to each other. For example, he jammed cobalt and nickel into the exact same slot and grouped them with halogens like fluorine and chlorine, which, trust me, behave completely differently. And bafflingly, he took iron, which is very similar to cobalt and nickel, and separated it far away from them.
So, as scientists kept discovering more and more elements, the writing was pretty much on the wall. The existing systems were entirely inadequate. So many elements just did not fit properly, and scientists were basically forcing puzzle pieces into the wrong spots. A much more accurate, flexible, and comprehensive classification was completely necessary to make everything fit properly and actually make studying chemistry make sense.
All right, let's lock all of this in. Section 5, quick revision and exams.
Okay, flashcard time. Think back to Dobereiner. If you see this exact question on your test, what exactly is a triad? Take a second, formulate the answer in your head. Got it?
To get full marks, you've got to write that it is a group of three elements having similar chemical properties, in which the atomic mass of the middle element is approximately equal to the average atomic masses of the other two elements. Remember, you absolutely must mention both the similar properties and that mathematical average.
Moving right along to our next vital question. Think about those musical notes and the atomic weights. Can you state Newlands Law of Octaves?
The perfect textbook answer is, when elements are arranged in increasing order of atomic masses, every eighth element has properties similar to the first element. Make sure you emphasize increasing order of atomic masses and every eighth element for sure.
And for our final exam question, let's evaluate the flaws. What was the absolute major limitation of Dobereiner's classification system? Why did scientists eventually have to abandon it?
The fatal flaw was simply that only a very few elements could be classified into triads. The vast majority of known elements just couldn't be grouped this way. Ultimately, organizing these elements is what made the modern study of chemistry possible. And even though Dobereiner's triads and Newlands' musical octaves had some pretty glaring limitations, they bravely laid the foundation for the future. Which leaves us with a massive, exciting question. If Dobereiner and Newlands laid a flawed foundation, how did Mendeleev's periodic table finally solve this ultimate chemical puzzle? Well, you'll just have to join us in the next explainer to find out.